Hey friends, it's Derek from TCI, and in this episode we're going to be talking about IP addresses. I don't have a script this time, I'm just going to talk from the heart, so if I screw up, you're going to have to bear with me. So, what are we talking about in this episode? We're talking about IP addresses. What are they and what gets them? And why do you want to know what they are? Learning about networking in general and IP addresses in specific makes you a rock star at your office. You can troubleshoot anything. And if you're a weekend warrior, it gives you all the confidence you need to tackle any networking project. You never know what device you're going to purchase that's going to require just a little bit of knowledge to make it fit efficiently and effectively into your home network. So what kind of devices need an IP address? You know, your phone, tablet, laptop, or desktop computers tend to have an IP address, but does anything else in your house need it? If you think about it, almost everything in your home that communicates in any way with the internet is going to have an IP address. As an example, you might have just a portable game device like a Switch. You might have a Steam Deck. If you've got a wireless drawing tablet like I've got, or if you've got a smart TV, smart thermostat, those smart light bulbs that do all the cool RGB colors, it's literally everything in your house that wants to communicate with anything else is almost certainly going to have an IP address. So how do these devices use the IP address? Many people will liken it to sort of a cell phone number. We know when we want to call one of our friends that we just have to punch their number into our phone and then we can make the connection between our two phones and have a conversation. It's very similar with the computers, where they'll each have numbered addresses that if I know the address of another computer, I'm able to pass messages back and forth between their computer and mine. In the same way that two people cannot have the same phone number, two computers cannot have the same IP address. The uniqueness on the network is what makes your computer locatable by other computers. If we have a duplicate, there's going to be some problems. For me, the phone number analogy kind of breaks down once you get into a little bit of a bigger environment where there's more than a couple dozen computers. It's a little bit more similar in my mind to street addresses. If you want to find or GPS your way and drive from your house to someone else's house, you need to know what city they live in, what street they're on, and their house number in order to find them. And there are a lot of similarities in that concept to the IP addressing schemes that are used by computers. Why don't I show you on my tablet what an IP address probably looks like when you check it on your computer. Most of the time, it's going to be 192.168.1 and then something. IP addresses are always 4 different digits that we call octets. And an octet has a value between 0 and 255. We've got 4 of them that make up our IP address. It's very similar to your cell phone where you've got 10 digits from 0 to 9. The IP address digits are from 0 to 255. If you consider them as 4 digits or 4 octets, they're very similar to a cell phone number in that regard. The same way that your cell phone is broken up into an area code and then your actual phone number, your IP address is also broken up between what's called a network portion and a host portion. In the IP networking world, everything that connects to the network and gets an IP address and communicates is called a host. And a host should have a unique number amongst all the computers on the network. The network portion is similar to your city name or your street name. You might have Main Street with 56 different houses along it, and that's similar to how the network operates when you're dealing with it in an IP address. Part of your IP address never changes. That part is called the network, and the part that does change is called the host. I'll get more into this when we do our lab in just a few moments. Speaking of IP addresses, why don't we go onto our computer right now and just real quickly check what IP address we have. If you're using a Windows computer, I want you to press the Windows key and then tap on the R. That should bring up the Run box. In the Run box, you can type CMD and press OK. This will open up the terminal. In the terminal, you can type ipconfig and press enter, and that will show you a list of all of your interfaces and whatever IP address is assigned to each of them. Remember from our previous discussion in another video that you can have more than one interface in your computer. Sometimes, even though you don't realize it, there are additional interfaces that Windows creates that you weren't expecting to see. Look for the one that says Local Area Connection. Now, if you're using a Macintosh, what you'll do is you'll press the Command button, then the space bar. That'll bring up the Spotlight search. Type in Terminal, then press Enter. That'll bring up a terminal very similar to the one that the Windows users get. However, the command is a little different. Instead of ipconfig, you're going to type ifconfig and then press Enter. Again, you'll get a whole list of all your interfaces on your computer, and each of them will have an IP address assigned or not. The main one that you're looking for is either your wireless connection or your local Ethernet connection. If you look at the output from either of these commands on either type of platform, you should see more than one piece of information. You have an IP address, and I'm willing to bet it's probably 192.168 something something, or you've got an address like 172.16 something something, or possibly your address is 10. something something something. It's going to depend a great deal on where you're doing this test, but if you're at home, most likely 192.168 is where we're going to start. In addition to the information showing your IP address, you should also see something called a mask. Your mask is an important piece of information that helps us determine what is the area code, or street number if you will, of the network that you're on. In networking terms, we use the mask to figure out which portion of the IP address is the network in order to separate it from which portion is the host. Let's take a closer look at the mask. I'm going to write it down here on my tablet, and then I'm going to compare it against the IP address. If you write down the IP and then the mask, and you arrange them so that they're one above the other so that the dots are aligned, we can do a little check real quick and see which ones of these are the host address numbers and which ones are the network numbers. Now, the mask is also broken up into octets, 4 of them, exactly like your IP address. In the beginning, when you're learning, the values of the mask will either be 255 for an octet or it will be 0 for an octet. If you look at the way that I've arranged them here on the tablet, the 255s line up with 192 and then 168 and then 1, and the 0 lines up with 101. That's how we tell which part is the host and which part is the network. So if I want to know what network I'm on, I count up all of the ones that are on top of the 255. So my network will be 192.168.1.0, and then my host will be 0.0.0 and then 101. That's how I separate which one of these is my network number, or street name, if you will, from the host number, or house number, if you will. If you imagine this as a street, the computers are all the houses that live along that street. Computers that have a network number in common are able to communicate with each other, and computers that have different network numbers are not able to communicate with each other. It doesn't matter, even if they're on the exact same switch together, if they're on different networks, they won't be able to ping or pass information between each other. In order to get between 2 different networks, I normally need to use a router or a gateway, sometimes called a firewall. This device's job is to let information into and out of my network. It can also bridge networks together so that I can pass information to computers that are on other networks besides my own. If you imagine a network as a sort of a gated neighborhood where we all live on a private street and there's a gate with a security guard at the front, the security guard decides who's allowed to drive on my street and who's allowed to exit as well. Kind of makes it more like a prison when you think about it. That's not important. In order for the guard at the security gate to let me onto another network, he needs to know where that is. If you imagine the security guard is in charge of a series of roads, if he has a road that I'm asking him to drive on and he doesn't know which gate to open to let me onto it, then he will either block my attempt from leaving or entering, or he'll forward my information, kind of dumping me on to the highway. And it's at this point that I've stretched this analogy to the absolute breaking point. Your router's job is to connect you between networks. If you think too much about how it might apply in the real world, you'll end up straining yourself. Let's come back to that later. Right now, I want to focus on where do these IP addresses come from? If you look at the format, we have 4 octets, but who picked these numbers and where do they come from? The 2 most likely places that you're going to pick these octets from is either you're going to make them up yourself, as I'm going to do in a lab in just a moment, or you've received them automatically when you attached your patch cord to the network switch or when you joined the Wi-Fi. You got that number directly from your router or firewall or gateway, whatever you want to call the device that's running the network that your internet's plugged into. What happens on that device is some software is running that is called the DHCP server, Dynamic Host Control Protocol. Whenever you plug in anything to the network, it sends a broadcast out and it asks, hey, can somebody give me an IP address? And what will answer is the DHCP server. In nearly all home networks, the DHCP server is running on your gateway or router. This software maintains a running list of which IP addresses it has given out and whether or not a device has not been seen in a while. If the DHCP server that's running inside your router hasn't heard from one of the computers in a while, it will eventually reclaim that IP address in order to give it out again. That's what makes it dynamic. It's pre-programmed into your router as 192.168.1, and then the range will be from, say, 100 to 200, and it will dynamically hand those out to whichever computer sends a broadcast upon plug-in, and then it will remember that for a little while. If the computer drops off the network and hasn't communicated in some time, the address will be reclaimed back into what's called the pool. It can then be doled out again to another device that later joins the network. Why don't we fire up a pair of laptops and do a quick lab? We're going to be using one Windows PC and one Macintosh PC so that we get a little bit of both platforms. We're only going to connect them with a switch. There's no router or firewall in this lab. And the reason for that is you will learn more if you manually do this. Let's dive in, shall we? Hey students, welcome to our lab. Okay, what we need to do the next few steps are one Macintosh computer and one Windows computer. You need one switch and one Ethernet interface on each of these computers. I'm not going to use a router in this scenario. It would mess with our lab, and it's not really what we're trying to learn right now. We're trying to learn about IP addresses, and a router is going to do a little too much for us. So in order to learn to do things by ourselves, we're taking it out of the equation. For my Macintosh, because there is no built-in network interface card, I've got a USB to Ethernet adapter, which I will attach to my computer. Let's get that going. And I'll then patch into that switch. Green light, good. Let's patch in our PC. Put that around the back. Green lights, good. Okay, we're going to do probably most of our testing inside the terminal. So I'd want to bring that up on both these computers. On your PC, it's Windows R. Then you type in CMD for command, press enter, and you've got yourself your terminal. On your Macintosh, it's Apple spacebar, then you type terminal, and then you press enter. The terminal window will appear. I'm going to resize this just a bit to make it easier to see. Now, before we get going too far and start testing, let's turn off our Wi-Fi. If we're joined to a wireless network, it's going to mess up some of our lab. On Windows, you click the wireless icon and you turn Wi-Fi off completely. And on the Macintosh, it's the same. You click the wireless icon and you turn Wi-Fi off completely. Okay, what I've done so far to start this lab off is all I've done is plugged my systems into a switch. There's no router, and I've done no configuration at all. Both of these computers already have an IP address. So let's start there. In order to view our IP address, it's ipconfig on the PC. You'll notice that it lists all of my available interfaces, most of which are wireless, some of which are extra from connectors that I've attached in the past. However, the main Ethernet adapter is the one that we are using right now, and that one's got an IP address, except we didn't give it one. So where does this IP address come from? This is called a PIPA. This is the automatically programmed, or provided, if you will, automatically provided IP address. It always starts with 169.254. Remember that series. If you see 169.254, it means that your system was unable to communicate with any DHCP server. There's a lot of reasons that that could happen, but in our lab, the reason is there is no router and there is no DHCP server running that would give away addresses. So what your computer does when it cannot find a DHCP server is it chooses at random an address in the 169.254 network, and then it broadcasts over the switch and it says, does anybody have this right now? If there's an answer from, say, this laptop that conflicts, then it will pick a new one and it'll try again. And it'll just do that over and over and over again till it finds a random address on 169.254 that's not in use. The Macintosh is doing something similar. It's also picked one of the interfaces to mean this USB to Ethernet adapter, and it's then assigned a 169.254 style address to that interface. In my case, it turned out to be EN8. So the effect of a PIPA is that without any configuration on my part, I can attach multiple computers to a switch, they'll assign themselves an address, and then they can speak to each other. Without a router, I might not have IP addresses and internet access, but if you think about it, on your computers, you still would probably want to be able to print, you'd want to be able to scan, you'd want to be able to stream things between two computers or access a file server, and a PIPA is what makes this possible. But we're not here for that. We're here to learn manually how to do things ourselves, so let's move on to that. On your PC, press Windows R again, and this time type ncpa.cpl. Press enter, and this will bring up your network interfaces control panel. In order to manually assign an IP address on Windows, all you have to do is find your Ethernet connection and double-click it. That'll bring up this screen here, and you'll look for properties. Under the Ethernet properties, you're looking for Internet Protocol version 4. Double-click that, and it will bring up the IP properties. It's currently set to automatically obtain an IP address. And that means that it is set to ask for a DHCP provided IP. But you can override that and use an IP of your choosing. So I'm going to pick 1.1.1.1. Why not? The subnet mask, when we're first doing this lab, not important. So I'm going to stop right there and just press OK. On my Macintosh, I'm going to do something similar. On a Macintosh, what you'll want to do is go to the Apple menu, then System Settings, then Network, pick your adapter, and then press Details. Under TCP/IP, it says using DHCP, but we're going to modify that to be manual. All I have to do is pick a different IP address than the Windows computer. So I'm going to do 1.1.1.2. For just this moment, I'm going to make the mask look like this. Now with that done, I'll go back to my terminal. Can my PC ping my Macintosh? The ping command tests for network reachability between two computers. When you type ping and then follow it with an IP address, all you're doing is sending one packet across the switch to the target, and then you're waiting for a reply. Let's go ahead and press enter, and we are in fact getting a reply. Let's go to our Mac and do the same thing. On our Mac, we'll type ping and then the IP address that we gave the Windows computer. We've run into a problem. There is no answer. Why would that be? Well, I'll get to that. First, we have to stop the ping. The ping works differently on Macintosh versus Windows. When you ping things on a Mac, it pings forever. You must press Control-C in order to stop the ping command from executing. So why am I unable to ping from the Mac to the PC, but I am able to ping from the PC to the Mac? If this is your first time working with this kind of troubleshooting and you're dealing with networks, the first thing you always want to look for is the Microsoft built-in firewall. So if you click your Start button and you just type firewall, one of the very first things you will see is the firewall control panel. So you want to get into that. One of your three networks, you have a domain network, private, and public. One of them will say active. Whichever one that is, click on that, turn off the firewall, close the warning about turning off your firewall. You can then close that control panel and then go back to your Macintosh. You can press the up arrow to retype any command that you've typed recently into the terminal. And if you then press enter, now we're getting a reply. I'll press Control-C in order to stop the ping command. The Windows firewall is a security measure that prevents your computer from being auto-detected on the network. However, it's not foolproof, but it's a good starting point. I'm turning it off for the purpose of this lab going forward because it's just going to get in the way whenever we're trying to do some testing. Now, let's talk about the address that I picked. Let's go back into both of our control panels and look at that address again. So I'm going to go to the Ethernet control panel. I'm going to bring up my properties, and then I'm going to double click on IP, and then let's take a closer look at what we did here earlier. When I told you earlier that IPs can be assigned manually, it gives you the complete freedom to pick anything you want. However, there are some reserved IP addresses that you should remember, and those are what we'll use for the rest of this lab. The reserved IP address ranges that we can use are 192.168, then a number of our choosing from 0 all the way to 254. I'm going to pick 1 as my network number, and then I'm allowed to use 1 through 254 in the final octet. And that gives me a network size of approximately 253 computers. I also have to change my mask to match. 192.168 is a reserved network pattern that allows me privately to create my own network. It never gets routed, and it's not allowed out on the greater internet. I can do the same thing on my Macintosh, 192.168.1, and I'll pick 1. Let's make sure that we can still ping each other. 192.168.1.1 is my Macintosh, and I'm getting a reply. 192.168.1.254 is my PC, and I'm getting a reply. Control-C will stop that test from running. Now, if you've done some networking before, you might have noticed that I picked IP addresses deliberately that would conflict with your home router. I do that to point out that the IP addresses themselves are not special or reserved and have no particular meaning. Your router could be assigned 192.168.1.2 or .3 or .anything. As long as your PC and your router don't conflict, it's all okay to do. The other reserved private IP address ranges are 172.16 through 172.31, which reserves 16 networks that are private. The number of hosts within that private network can be up to 16,382. The third reserved private IP address range is starting with just 10, and then everything after the 10 is chosen by you. That's 16 million hosts, and you can carve that up however you want into smaller networks. Now, for lab purposes, let's start screwing around and making a mess. On the PC, I'm going to go and change my mask. Let's create a situation where the mask on the PC does not match the mask on the Macintosh. So without changing my Macintosh, I'm going to try and send another ping. And it still works. Perhaps that confuses some of you who have had network experience in the past. Normally, when your masks don't match, there's a problem. But just now, they work just fine. Why do you suppose that is? Well, the main reason in this case is luck. I happened to pick something that still fit within the network of 192.168.00 in this case. 192.168.1 is still valid and would look like to this PC that it's still in this network. However, if we were to change one digit, let's give that a try. I'm going to change the third octet to a 2 in this situation. Then I'm going to go to my Macintosh. I'm going to try to ping that. Now I don't have an answer. And the reason is I don't have that luck anymore. I've picked an address from my Macintosh that is outside of the network of my PC. If I modify my Macintosh to have 0 for the third octet, it will respond again. Let's give that a try. Now the ping works. So what effect did that just have? If you look closely, when I modify my network mask, I'm changing which parts are the network and which parts are the host. If I add another 0, my host is made up of the last 2 octets, and my network is made up of the first 2. When I had them mismatched before, I put myself out of the network. Even though these are on the exact same switch together, and they're literally right next to each other, IP packets are dropped if you're on a different network from your source and target. The only way to get between networks is to have a router helping you out. Without a router on this network, we end up unable to communicate because the networks are different and the software will drop unfamiliar packets from outside of its own network. Now, without changing anything else, let's do another test. We want to ping 127.0.0.1. And I get a reply from that IP address, even though I've not assigned it to any of my computers yet. If I go to my Windows machine, it's the same. 127.0.0.1. So what are these things pinging, and why are we getting an answer? 127.0.0.1 is reserved, and it is a shortcut or a way to say ping myself. Another way you could do that is just type in ping and put in your own IP address. If you put in your own IP address, you should always get an answer. When you think about it, when you join the network several times a day, put your computer to sleep, open it again, take it somewhere out of the house, bring it back to the house, it's joining and rejoining the network repeatedly, right? And if you've got a DHCP server in your system, you might get a different address several times throughout the day. And if you've got a scenario where your software needs to run and have a consistent IP address to use to talk to itself, 127.0.0.1 always means you. Now what happens if I go outside of the reserved range like I did in the beginning, just using all ones? If I don't use one of these reserved IP addresses, like 192.168, what if I pick something public, like 67.53.86.12, and I got creative with the mask, and I did something like this? What would be the effect? Your two computers would still be able to communicate because they've got their switch between each other, and if I put them on the same network, the pinging will work. And if I then attach a router, and I gave the router that same public IP range, and I used it for my private internal communications, that would still work, but there'd be a side effect, and it's a pretty serious one. Huge swaths of the internet, like millions, tens of millions of computers, would become inaccessible because my router would erroneously think it knew where all those IP addresses are. It thinks that they live here on this side of the router, when in reality, it belongs somewhere out on the internet proper. Not using the reserved IP addresses will really screw up your ability to browse the internet.
That's why you've got to stick to those whenever you're setting up a home or small office.
Okay, I'm going to pause the lab right there because we need to add in a router if we want to get any more fancy than we are right now. So I want you, when you get your chance, go home, fire up one of your stations, nothing super important, take it off your routed network, plug it into a switch, and see what kind of trouble you can get into. It's very important to know all the little ways that you can screw up. The mask mismatch is a big one. Picking a non-standard IP is another big one. Conflicting with your router is another big one. And then not knowing the ins and outs of your operating system is a huge pitfall. So you want to get all of that tested and out of the way. So if you've got Linux at home, maybe you're using a Raspberry Pi or something, try to do some of the same steps and see if you get the same behavior that we got just now between these two computers. I'm going to finish up by turning my firewall back on, and then I'll see you in the next lab. Thanks, everyone.